Okay, this is 2.6. This is dealing with graphs of some functions that you may or may not have seen already. So think about this section as preliminary for the next section, for 2.7. Right now, in this section, we're going to talk about various types of functions and some properties of functions, so that in this next section, in 2.7, we can do transformations of graphs of functions. Okay, so let's get going. The first thing, one of the first properties about graphs of functions is, the first thing we're going to talk about is called symmetry. So we can have three types of symmetry. Symmetry with respect to the x-axis, symmetry with respect to the y-axis, and symmetry with respect to the origin. All right, let's talk about the three types of symmetry. So let's begin with symmetry with respect to the x-axis. So if a graph has a point x comma y, then the point x comma negative y should also be on the graph. Here I sketched a little example of something that's symmetric with respect to the x-axis. This is a sideways parabola. Its equation is x equals y squared. And notice that this is not a function. So if you have symmetry with respect to the x-axis, you are not dealing with a function. So in this equation, x equals y squared, if my x happens to be 2, turns out that if my y happens to be 4, I have two, so I have the point 2 comma 4, but I also have the point 2 comma negative 4. So that's kind of what we were saying here. If the point x comma y is on the graph, then x comma negative y is also on the graph. So if 2 comma 4 is on the graph, and this thing is symmetric with respect to the x-axis, then 2 comma negative 4 should also be in the graph of my function. But it's not in the graph of this relation, and it's not a function. If you're given an equation, so if you have an equation like this over here on the right hand side, x to the 4th plus y squared equals 7, and you do not have the graph, let's say you do not have the graph, and you're trying to test to see if it's symmetric with respect to the x-axis, what you should do is you should replace your y's with negative y. And if after you replace y with negative y and simplify, if you end up with the same equation, then you're dealing with something that's symmetric with respect to the x-axis. So for instance here, I replace my y's with negative y. I put a parenthesis about this negative. I'm squaring it. A negative squared becomes positive. So then once I simplify, I end up with the exact same equation. So I can be certain that the graph of this equation is symmetric with respect to the x-axis. And it's not a function. Okay, now let's talk about symmetry with respect to the y-axis. Okay, so if x comma y is on the graph of my relation, then negative x comma y should also be in the graph if my graph is symmetric with respect to the y-axis. All right, and this is the quintessential example of being symmetric with respect to the y-axis. The equation y equals x squared. That's our parabola. And notice here that I have the points, I just noticed that I need to change some signs here. So I have the point 2 comma 4, and so I should have the point negative 2 comma positive 4. Here I have the signs switched. So let me correct that. That's a positive. Let me erase this little parenthesis here. So let's say negative 2. There we go. Okay. This is a function. This passes the vertical line test, whereas the previous one does not pass the vertical line test. That's why it's not a function. So anything that has symmetry with respect to the x-axis is not a function. This one is symmetric with respect to the y-axis, and it's a function. whenever we have a function that is symmetric with respect to the y-axis, we call that function even. It has to be a function. If it's not a function, then we cannot call it even. Because there are other equations that are symmetric with respect to the y-axis that are not functions. Think about what that would be. All right. Another guideline for figuring out when a function is even is, this is using function notation, is that if f of negative x equals just f of x. That's what it means for a function to be even. So if a test to see if a function is even, what you should do, I mean, let's say you have the equation but you do not have the graph, then just change your x's to negative x and then simplify. And if you end up with the same equation that you started with, then you're dealing with an even function. So in this case, I replace my x with negative x, I squared, a negative squared becomes positive, so it just ends up being exactly the same as before. So this function is even. And remember, this word even and odd only applies to functions. All right. This is weird here. Symmetry with respect to the origin. There's a couple of ways to describe it. Well, let's just begin with what we are being told here. If x and y is on the graph, then so is negative x and negative y. So for instance, here I have my example of an odd function, y equals x to the third. Here's its graph. And notice that I have the point 2, 8. So if my x is equal to 2, my y is equal to 8. So I have the point 2, 8 in my graph, but I also have the point negative 2, negative 8. Yeah. Another way to think about an odd function is imagine that you had like a nail or a pin and you put it right at the origin and then you rotated your graph 180 degrees. Does it land back on itself? Does it look exactly the same as before? So think about, imagine that you could sort of fix the origin with like a nail or a pin and that your graph was movable and you could rotate it 180 degrees. Does it land back on itself? I would say that this guy does. That would be another way to maybe see if a graph is odd. So first of all, this is a function. It passes the vertical line test. So we can use function notation for this equation, and we're going to say that this function is odd. A test to see if a function is odd that involves function notation is to say that if that f of negative x is equal to negative f of x. All right. Now, if you didn't have the graph, all you had was the equation to go with, and you wanted to know if you are dealing with an odd or symmetry with respect to the origin. So if you want to know if you're dealing with symmetry with respect to the origin, you change your x's to negative x, and you change your y's to negative y. So for instance, they gave us this equation right here, and we want to know if it's symmetric with respect to the origin. I change my x's to negative x, I change my y's to negative y, squared, if I square negatives they become positive, I end up with the same equation. So this equation, the graph of this equation is symmetric with respect to the origin. And the graph of this equation is just a circle centered at the origin of radius square root of 5. And so this is, notice here that this is not a function. This is not a function. So not odd. We can only speak of even and odd whenever we're actually dealing with functions. Okay, so symmetry with respect to the x-axis, symmetry with respect to the y-axis, symmetry with respect to the origin. Let's move on. So in this next part, we're just going to talk about some graphs of some basic functions. Some of these functions and graphs you've probably seen before, and maybe there's a couple that you haven't. There's only one exercise in this section. It's towards the bottom. Right now we're just going to go through some known functions. So the first function that I'm going to begin with is just y equals x, or f of x equals x. That's this diagonal line that happens to go through the origin. That's just my very simple line. The domain of this line is negative infinity to positive infinity. The range is also from negative infinity to positive infinity. And I'm going to say that this function is odd. This function is odd. It has symmetry with respect to the origin. Imagine putting a pin right at the origin and rotating the graph 180 degrees. It looks exactly the same. Okay, the next function is our trusty parabola, y equals x squared, or f of x equals x squared. We've already said that that is an even function because it's symmetric with respect to the y-axis. Its domain is negative infinity to positive infinity. Its range is from 0 to positive infinity. The domain deals with the axis, so this goes from negative infinity to positive infinity. The range deals with the y's. The lowest that my graph goes is to 0 and all the way to positive infinity. All right, so let's build our repertoire. Remember, we need these functions and graphs so that in the next section we can transform them. Okay, my next function is y equals square root of x, or f of x equals square root of x. Remember, we cannot plug in negatives. We cannot plug in negatives inside even roots. So then the domain of this function is only from 0 to positive infinity. It doesn't exist for the negatives. And its graph reflects that. The graph begins right here at the origin and sort of slowly goes up. So then the domain is 0 to positive infinity. The range is also from 0 to positive infinity. All right, and this graph is neither this graph is neither even nor odd. It doesn't have symmetry with respect to the y-axis. It doesn't have symmetry with respect to the origin. It doesn't have any type of symmetry. All right, another function and its graph, the cubic root of x. Y equals cubic root of x, or f of x equals cubic root of x. And by the way, remember that we can also use exponents to express this. We could say that this is x to the 1/3. All right, this is the domain of this function is from negative infinity to positive infinity. It is okay to plug in negatives inside odd roots. For instance, what's the cubic root of -8? Well, it turns out it's -2. So this function does go into the negatives. So its domain is from negative infinity to positive infinity. Its range is also from negative infinity to positive infinity. It's very similar to the graph of the square root of x. It's just that this one does have this little tail that goes into the negative x-axis. All right. A couple more functions here. X cubed. We already talked about x cubed. We used it as an example of an odd function. We know its domain is negative infinity to positive infinity. It's odd. Its range is also negative infinity to positive infinity. The next function, the absolute value of x. Y equals absolute value of x. F of x equals absolute value of x. That's this v. It's actually a piecewise function. The absolute value function is a piecewise function. We'll talk about piecewise functions here in a second. Or let me just kind of write it down here. You can think of the absolute value function as a piecewise function. It's x if x is bigger than or equal to 0, and it's negative x if x is less than 0. That is what the absolute value function is. And this function is definitely even. It has symmetry with respect to the y-axis. Its domain is from negative infinity to positive infinity, and the range is from 0 to positive infinity, because that's how low my graph goes in the y-axis. All right, so hopefully you're somewhat familiar with all of these functions and their graphs so far. Now let's get into maybe a new function here. I don't have too much space here, so 7. I'm in this graph number 7. I kind of went over here to the right hand side because I do not have enough space here. So this is the function. It's called y equals, and then there's these weird brackets, and then there's an x inside. So there's these little weird brackets. This function is called the greatest integer smaller than x function. Greatest integer smaller than x. I guess let me say function. All right. So how does this function work? So you give me an x, the output, so the input is some x, the output is going to be the greatest integer. Integer just means whole number smaller than the input x. So if my x happens to be -2, my output is just -2. Now, if my input, let's say, is -1.3, so if my input is -1.3, what's the greatest whole number smaller than -1.3? Well, that's -2. Yeah, so think about that for a second. With negatives, it might get a little confusing, but just think about it. It's the number that's to the left of -1.3. What's the number to the left of -1.3? The whole number. It's -2. What is, so if my input is -0.32, so -0.32, what is the smallest integer? So what is the integer to the left of -0.32? The greatest integer, I guess it's -1. If my x is 0, my y is 0. If my x is 0.32, what's the greatest integer smaller than 0.32? Well, it's 0. It's still 0. If my x is 2, my y is 2. If my x is 2.3, the greatest integer smaller than 2.3 is 2. And I hope this graph makes sense. So the graph actually is, it's kind of like a piecewise function. So it's we have the graph over here. This little pattern keeps on going forever. So for instance, the next little thing would be something like this. The only thing is I do not have enough room here to sketch these little things. It's kind of crowded, but you get the idea. The open circles represent that that point is not included. The closed circle means that the point is included. So it looks like little steps. These graphs are kind of useful later down the line. Sometimes these types of graphs act like switches. So you turn something on, you turn something off. That's this big kind of jumps and gaps that happen here. So they have some usefulness in computer science and electrical engineering. Now, what's the domain of this function? What values can I plug into my function? Well, it turns out anything, -infinity to +infinity. Now, what's the range? What's the outputs that I get? The outputs are just integers, whole numbers. So things like -2, -1, 0, 1, 2, and so on and so forth. So that's the range of this function. This is a weird function. Remember, the name of it is called the greatest, and let me put a T here, greatest integer smaller than x function. Okay, last little thing in this section. Let's actually work out an example now. So I know it's kind of hard to see. What I want you to do is I want you to graph a piecewise function. Yeah, I've given you here a piecewise function. It's kind of hard to see, I know. It's y equals f of x, and then the top line says -1/10 x squared plus 6. That's for x's less than or equal to 2. And then in the bottom line, I have 1/10 x for x's bigger than 2. I kind of want to see the graph of this thing, and I'm going to ask you what's the domain and what's the range for this graph. So if I was you, I would pause this video, take about 5 to 10 minutes and see if I can come up with the graph on my own and answer the question of what is the domain, what is the range of this function. Okay, let's try to sketch this function then. Let's begin by sketching it. I think if we can sketch it, then figuring out the domain and the range becomes a lot easier. Let me begin by thinking about the graph of the top part. So right now, I want to analyze the graph of this part right here, the negative 1/10 x squared plus 6. All right, so let's see. I'm going to say y equals negative 1/10 x squared plus 6. Right now, I'm not too worried about the for x is less than or equal to. Right now, I just literally want to know, what does this graph look like? Yeah. Well, it's a parabola, right? It's a parabola because we have x squared. Not only that, but I'm getting ahead of myself a little bit here. This negative right here, the negative, makes my parabola turn upside down. So it's a parabola that points downward. This 1/10 here in front of my x squared, that is a vertical shrink of sorts. We'll talk about that in the next section. And the plus 6, what it does is it moves my parabola up 6 units. Originally, if you remember back at the parabola, there's a special point down here called the vertex. The vertex is at the origin. What this plus 6 right here does is it moves my vertex 6 points up. Okay, so another thing that I want to do just to make a better sketch is I want to find the x-intercepts. So I know that this parabola, or I mean, think about it. How do I? Let's say I wanted to find the y-intercept of this equation. To find the y-intercept, I set my x's equal to 0. So this part would be 0, and it just says that y equals 6. So my y-intercept is at 0,6 right there. Now let me find the x-intercepts. So I'm going to set my y equal to 0 now. And let me solve for x. So then that means I need to subtract the 6 and multiply by negative 10. So that's going to give me 60. All right, and then I have to take a square root, and that's going to give me two things. It's going to say x is equal to the square root of 60, and x is equal to negative square root of 60. Yeah? And I know that the square root of 64 is 8. So I know that the square root of 60 is less than the square root of 64, and this is definitely bigger than the square root of 49. So this is 7, this is 8. So the square root of 60 is somewhere between 7 and 8. Yeah, it's like almost 8, I think, 7 point something. So 5, 6, 7, somewhere around here is one of my x-intercepts. Negative 6, negative 7. Somewhere over here is another one of my x-intercepts. And so now what I have is a parabola. Let me join this these 3 points as best as I can with a parabola. All right, so that is the graph of negative 1/10 x squared plus 6. That's the graph of negative 1/10 x squared plus 6. But I do not need the entire graph. I only need the piece that's x is less than or equal to 2. All right, so let me go to x equals to 2, where x is equal to 2. So I'm going to write it right there. And x less than or equal to 2 means that it's all of the points somewhere. So let me put a dot here on my graph. And this is saying it's all the values to the left of there. So I do not need this right piece anymore. I just used it to sort of get me going. Yeah? All right. Now in green, I'm gonna draw the other one. Now let me think about what does the graph of y equals 1/10 x look like. That is a little bit simpler. That's just the equation of a line. This is in slope-intercept form. This is the slope. The slope is 1/10. The y-intercept is 0. So the y-intercept is right at the origin. And the slope is telling me to go up 1 and to the right 10. All right, so this is an almost very horizontal looking line. So some situation like that. Yeah. And well, now I only need 1/10 x only for values of x that are bigger than 2. So I do not need anything that is less than 2. So let me erase this part. And actually, I'm gonna put an open circle here, because the inequality is telling me that that point is not included. Yeah. And so I think that is what, I mean, that's an ugly little sketch of my graph, but I think that is what my graph looks like. I hope that we agree. Now, let me answer the questions of domain and range. What would you say the domain of this function is? How far to the left does this keep on going? I'm gonna say from all the way to negative infinity. It keeps on going. Right here, there's a situation here, right at 2, at x equals 2. Remember, the domain is talking about x values. The value 2 is not included on the green graph, but it is on the red graph. So it is included in the piecewise function. And so I'm going to say that the domain of this thing is all real values, negative infinity to positive infinity. It goes all the way from the left to all the way to the right forever. What about the range? How far down does my graph go? How far down does this graph keep on going? Well, this left part just keeps on going down forever and ever and ever and ever. So I'm going to say that my range goes from negative infinity to, how far up does my graph go? What's the highest y value that it ever achieves? Are you going to say that it's 6? I mean, that's what I see right there, that it should be 6. But you see, that's the only, right now I'm focused on a little piece of my graph. I'm just zoomed in kind of near the origin. Think about this green piece right here. I mean, yeah, it goes up 1 and over 10, and then up 1 and over 10, and then up 1 and over 10, and then up 1 and over 10, and so on and so forth. Eventually, that'll become higher than 6. This green part actually goes towards positive infinity, very slowly. But in the long, as my x's grow more and more and more and more, the graph will go higher and higher on the y-axis. So I'm going to go ahead and say that this graph also has a, and if you're thinking, wait a minute, what about the gap right here? There's a big gap right here of y values, right? But look at them, they're over here. They're included in these pieces right here. So the range is also from negative infinity to positive infinity. And that's it. That is all for this section. All right. So thank you, and I'll see you in the next video. In the next video, we're going to be using some of these functions to talk about transformations. All right. Thank you.